this week, so please, whenever you're ready, take it.
Okay, thank you. So thanks for the opportunity to come. The objects that I'll be I introduce some motivation and some theoretical framework with some more complicated objects, but ultimately the objects that we are discussing today are eigenvalues and eigenfunctions of finite matrices. So I'm trying to say something interesting about eigenvalues and eigenfunctions of a finite matrix. It's going to be a joint work with David Damanik, by the way. So you have a finite matrix, but very large. So it's a very large finite matrix with many coefficients. And you can ask, so then there will be a lot of eigenvalues and a lot of eigenfunctions. Some people are interested in trying to understand how did they distribute in certain contents. Once n is very large, that's a very common question about eigenvalues. It's discharged a lot when you consider random matrices, if the matrix would be coming from some random distribution and so on. So this is a point of view. I will be more interested actually on the eigenfunctions associated to this, and I will look at specific, so normally people could consider this unitary matrices. You'd put in some self-adjoint matrices of certain class, so you'd introduce some thing. I consider some that are coming from some natural objects, so the ones that are of relevance in directly on some models of condensed matter in quantum mechanics. So what's the situation that, so what's the basic kind of myths that I will consider? I'm going to consider the Schrödinger operator. So to help get ideas, you can think that the Schrödinger operator uses a space ZD. That's my space, so that it's a discretized space. Or I will work also in a discretized, in a bounded case. That's the case that most interests me. N is a large number, and I consider just this kind of discrete set, and I will work on this box. This would be my space. So this is you imagine that you have some material here. So this is a box of material that is made of many tiny pieces, and I discretized it, and I got this this expression. And how's the Schrödinger operator? So what happens in quantum mechanics? You have a state of your systems is given by is a unit vector in this space. Let's say, for instance, this or the other or ZD, and you make it 2 norm to be 1, right? So this is a state. It's interpreted. So in the interpretation, imagine that if I measure my system, then the probability to find, so this could be an electron lives here, I don't know. And then when I measure, I find my electron with certain probability at a certain site. So I discover where I am. Finally, after a measurement, and that gives the probability distribution. This is a complex Banach space or a Hilbert space, but you need to take the square and so on. So this is standard. I hope that. Anyway, so that so how does this? What's the equation of evolution for quantum mechanics? Is the Schrödinger equation. So that in time t, my state evolves like this. Right? It's a unitary evolution where H is a self-adjoint operator. So it's a self-adjoint operator, so this will give a unitary evolution. But so it's a special equation. So the Schrödinger equation will take this form where there is this is the discrete Laplacian, right? So you take the interaction near neighbors, and you do this. This expression here is a Laplacian, just discrete. Plus this diagonal term, so that's how you express or maybe this is minus a Laplacian, I don't know. And this is the potential. So I think that this Laplacian here quantize the kinetic energy, and this would be the potential energy of your system. I don't care about the physical terms, but you have this self-adjoint operator. If, for instance, my space was one dimension, then it's easy to draw this matrix, so that the matrix just looks like a three-diagonal matrix with ones near the diagonal and v's in the diagonal and otherwise zero. So it's a three-diagonal matrix. There is this freedom in the diagonal, otherwise I have those ones. And there is a -2 also because of this, but forget it. So there will be a v -2 maybe here. Anyway, so I have this basic setup. And what and you can also consider this into the infinite Hilbert space. It could be also L2 of ZT, right? And what are the many questions? So you're interested in this quantum dynamics, and one of the most basic questions that appears related to this is the issue of localization. So for this, I will introduce, I will start the discussion into this model because it's easier and more qualitative than quantitative. So basically, let me talk about a theorem. So there is the Anderson. So in this case, you take, so it's L2 of ZT, and V you choose it uniformly and independently. So you just take a random, at each site of my space, you put a random potential. So motivations like, I think that what I was thinking, let's imagine that my space was just some nice crystal, some nice material that I start with, and then some impurities appeared in my material, which I don't know how to describe. So I just describe it as a random impurities that are added. And his question is what happens. So the initial material without potential, so without, when V equals 0, you just have the Laplacian you can solve this this thing, so that basically there will appear a heat kernel and so on. The spectrum here is absolute continuous. There are no eigenfunctions, right? It's kind of a little bit obvious that that it is in this case, but there are no eigenfunctions for this, and it's actually the spectral measures absolute continuous. So the evolution of my initial states, it's possible to see that it it tends to go away. So the probability. So because of this, if I look at my initial state, right, and I try to correlate with some other state, this goes to 0 for this case of absolute continuous spectrum. So in particular, my particle, after time passes, I don't find it in the same position as it was before or near where it was before. It has to decorrelate with whatever. So that's just initial situation, but then he has this theorem that, so what's the theorem of Anderson localization says the following, that for d equals 1, right, and for every lambda, right, the random V is localized, meaning there is a full basis of eigenfunctions. So it's a different behavior. Because what happens now, so I described what was happening for the Laplacian when the spectrum was absolute continuous. So if you have a full base of eigenfunctions, this implies that the quantum dynamics is almost periodic. Right? The closure of the orbit of any vector will be a group, right, a compact group, and you are going to be just a translation on this compact group. What happens is that you have my state, I can decompose it over the base of eigenfunctions, and each projection will just rotate. And they have less and less important. There will be a sequence, is a superposition of modes that are increasingly of little importance, but you're just adding a quasi-periodic motion on top of quasi-periodic motion, but still you get a translation of a group. In particular, so this is almost periodic, so this is a compact, so the orbits are pre-compact. Which implies in particular that the probability, so what does it mean to be pre-compact in a Hilbert space? To be a part of the unit sphere that is in a compact set in the Hilbert space. It means that the probability of finding yourself in a bounded box, so for every epsilon, so compact set, for every epsilon, there exists some L, right, such that the probability of finding my thing in a box that has bounded by L, so a bounded box, is high. For every epsilon, I can find this L. So this classifies a compact set in the unit sphere of the Hilbert space, right? Is it clear? If I have a set in the sphere that's pre-compact, then I can find this. For every epsilon, I can find that L, and vice versa. If I have this, then it specifies whatever. So in particular, for all times, my quantum evolution, in case I have in this localized sense, it is localized because it means that for all times, I have high probability of finding myself in a certain fixed region of space. I have not kind of just went out to infinity. I remain in some place. So that's why you have this notation. And this is true in one dimension. It's proved that if d is any and lambda is sufficiently large, depending on the dimension, then also full localization. And it's proven that if d is bigger or equal than 1 and any lambda, then there is some partial localization, which means that there are some eigenfunctions. But you don't know if all of them, if there is a full base of eigenfunction. It's one of the most important questions in this whole field, is the problem to know what happens if higher d and the small disorder. Can it appear more things than just eigenfunctions? It's not known. It's believed by some that the answers change between dimension 2 and 3. So some people, some physicists believe that for dimension 2, it's still going to have full localization for all disorders, but starting on dimension 3, it should depend on the amount of disorder. So there are no theorems about that. The only theorems that exist are the ones that I plot on the blackboard. So there exists full localization dimension 1, full localization for high disorder on any dimension, partial localization for small disorder. All right, so that's the situation. And now, I think that those infinite dimensional spaces are very complicated and maybe not realistic, because maybe it should be just finite dimension, everything, and you should just work with finite dimensional space of very large dimension.
Can I ask a question? See, I mean, this e to the IH is just some unitary thing, right?
Yeah.
And it's got the v in it. So I thought all unitary things looked alike. So you're telling me that they don't look alike.
I can, it's actually, they have a lot of personality in infinite dimensions.
So tell us about the personality.
Yes, so it's convenient for people that do dynamics to remember what happens to the Koopman operator. So the Koopman operator, you have a dynamical system that has an invariant measure and a probability measure, let's say. And then it acts on L2 of this probability measure by composition. Right? And then this is just a unitary operator. Now, if there exists a basis of eigenfunctions, so this is the Koopman operator. If there exists basis of eigenfunctions, then the dynamics are almost periodic. So the dynamics is measurably conjugated to a translation on a compact abelian group.
I mean, the original
This is the original dynamics, and it's measurably equivalent, so it's a measurable dynamical system that is an invariant measure. I can conjugate it to a translation of a compact group with the Haar measure. Right, so it's very simple. It's an isometry. There is no chaos because the dynamics is isometric after you change the coordinates. On the other hand,
so all of the dynamics is in there.
it's coded. There is still some more personality than just the measurable aspect, but the measurable aspect reduced entirely to this. And now, if there are no eigenfunctions at all, this is equivalent to the notion of weak mixing. So it's an orthogonal notion to almost periodicity is weak mixing. It was developed by Furstenberg, which means that essentially there is decay of correlations on so if you integrate this, so those are correlations, dmi, I guess, and then this decays in Cesaro. So this goes to 0. So there is decay of correlations in Cesaro, which is orthogonal to this. If the spectral measure is absolute continuous, this implies, it's not equivalent, but it implies mixing. So you don't need to take absolute values here. So there is a lot of things that about the dynamics that are told by these spectral interpretations. Not all of the dynamics have some spectral component. There is more things. There is entropy. There are more personalities to think. But part of it is just.
What is the Storm's property in terms of the spectrum, in terms of the correlations?
This?
It's just
This is mixing. You don't need to take Cesaro average. It just goes to 0.
individual must go to 0.
Yeah.
Okay.
So this is mixing. So you see, so this is about the same. So what's happening here? So infinite dimensional space have this behavior. Now, what happens in high dimensional? I want to look at, try to understand now quantitatively what happens for large n. So what is, how to understanding localization in finite dimension. So now, of course, there are eigenfunctions, right? You have just the spectral theorem in finite dimensions. But some eigenfunctions are more localized than others, and these you can measure. So an eigenfunction with a high peak, you can imagine that I'm trying to pass to the limit. So suppose that I'm making approximations of my Hilbert space with infinite dimension by taking some large piece of my space and passing to the limit. If I had an eigenfunction, some eigenfunctions that have the higher peak, so a L2 function, So the norm was 1, but in some site it was bigger than, let's say, 1/3 or 1/10. As n goes to infinity, I could take the limit of this eigenfunction and it would resist somewhere, and there would be an eigenfunction for my thing. So basically, if the peak of the eigenfunction doesn't go to 0, it's something that would resist in the limit. So I take this as my concept. So phi is delocalized if the peak of phi, so I can measure it in the infinite norm, is close to 0. So phi is, I normalize in L2, but then I want the infinity norm to be small.
Phi is an eigenfunction.
Yes, an eigenfunction that's a unit eigenfunction. I will interpret it as delocalized if the peak would be small. And actually, for technical reasons, I will take a measure that's equivalent to this. It's just the fourth norm. This is small if and only if this is small, because this one is set to 1, right? So just some normalization. And but now I have a base of eigenfunctions, so I'm going to have many eigenfunctions, and some of them might be localized and some might not be. So I put a measure of localization for the operator. I look at all eigenfunctions and look at the average localization. So the operator has n to the d eigenfunctions, and then it should be sum of phi j so this would be my omega.
So that's a 4 you're writing? That's 4?
4. So this is between 0 and 1. So since this is 1, this 5, 4, 4 is between 0 and 1. It's close to 0 if the maximum is small. It's not close to 0 if the maximum is not small. Okay, so that's the definition of this measure of localization. And this is like, let me mention, this is not well defined if there is multiplicity in the spectrum, because then I have to choose a basis, right? There is a better way to define this in terms of spectral measures, which coincides with this definition when the spectrum is simple. So for spectral measures, so spectral measure formulation, so you can pick the spectral measure associated to the Dirac function over a site n, right? Delta n, this is just the basis of, the canonical basis of my space. And then it has a spectral measure, sigma n spectral measure, right? And then basically it is going to be the localization of the measure would be this. So this is a probability measure. This has the norm 1. Is sum. So it's the sum of the atoms square. So this is less than 1 because the sum of the atoms is 1. And then you also average with respect to everything. So you average over all spectral measures the localization of the spectral measures, and this is equal to that if the spectrum is simple. Otherwise, this is bigger or equal than that. This is basically, when I compute this, it's like taking a matrix and summing first over the columns, or rows, I get confused, and then summing over the rows, and here's the opposite. So you first sum over one and sum on the other. It's the same, there is a measure of localization. And there is a theorem with David, right? So for every dimension, the theorem works on any dimension, right? Any lambda also. So given me some delocalization that I want to achieve, there exists there exists some size that so of course if I am in finite dimension, if n is fixed, I have a box of a fixed size, it's just a finite matrix. That you have some localization or delocalization, I cannot do much. But suppose I'm interested in doing when my space is very large. So I have a very big box, or when I discretize it a lot, when my Planck constant was small, well, who knows. So then as long as I have enough space, I have the following theorem that for every V for any potential that I give, there exists a perturbation such that which achieve the delocalization to level epsilon. So I can make an arbitrarily small
What's that symbol? W?
omega of W. Omega is this.
Okay.
So this theorem says that as long as I have enough space, n is sufficiently large, then I can just perturb a little bit my potential such that the new Hamiltonian that I got, it has this delocalization property. Most eigenfunctions, now they have small peaks. That's what I wanted to do, and that's what is done. So that's the theorem. It has a lot of quantifiers, but those are the right quantifiers. It can be shown that they are the right ones. All right. Now, it's possible that so this will be proved by some optimization idea, right? I'm going to really think of this as an optimization problem. There is some quantity that's this one that wants to be made small, and I have to make it small somehow. I have difficulties to do that because the random case is localized. So as a consequence of Anderson localization, a typical V, right, will satisfy omega of V is bigger or equal than C of the D and lambda, let's say, bigger than 0. So a typical V will have some measure of localization because of that theorem. That is a finite version of that theorem, says that if I take a random operator in a big box, I will have some localized eigenfunctions, and then I'll be away from 0. So most places that I look, they look localized to some measure. And I still want to find a special way, deterministically defined way, to make it small, the localization measure. So that's, I can imagine that I have obstacles, all this localization, they are everywhere. I'm in a high dimensional space, and I have to find where to change my potential to achieve this. So, and I look at the optimization, a deterministic optimization problem. I need to find some special kind of flow that will delocalize. That's the goal, at least the inspiration of the thing.
So, for each potential, you have your eigenfunctions.
For each potential, I find a base of eigenfunctions. It has some localization type.
Perfect. And the eigenvalues, they have some continuity property.
The spectrum depends continuously on everything in finite dimensions, quite obvious.
So you are showing that the eigenfunction really is continuous.
The eigenfunctions change, everything changes, but there are many of them, like there are many. They can't change fast under certain circumstances. So you're comparing how fast, like there are many quantifiers. The main one is that n went to infinity, so it means that you have a lot of eigenfunctions together, or a lot of eigenvalues together, and the eigenfunctions are almost interacting.
Okay.
So if you have an eigenvalue that's far from the others, then everything related to this eigenvalue will change smoothly under perturbation. But if you have eigenvalues that get closer together, then they feel their interaction, and then you can try to pass one eigenfunction over the other. So this could be motivation, but you have to put a lot of eigenvalues together, so you need a lot of space, right? Okay, so let me say some words that are nicer.
Okay, so but this is the mechanism that you're going to do in a way to produce this dramatic drop of the localization measure.
Yeah. So I will profit this opportunity to talk about something easier and nicer, because the proof is, we have one proof, so the proof that, the first proof, the one that's still not available but will be soon, is use an idea that appears many positions, that sometimes you want to prove a quantitative statement about a finite statement like this one, about finite matrices, and the easiest way to prove it is to go to an infinite dimensional limit, to work on an infinite limit. And one of the examples that's more famous about that is the Zemeradi theorem. So since everybody knows this and people like listening to what they know, I mentioned it. So the Zemeradi theorem, and somehow it's related to our theorem. Well, at least the principle. So the Zemeradi theorem is a finite theorem, right? What does it say? It says that if I have a set X contained in my space N, so N is just 1 to N, and X is contained in N, and so let's do it. So for every epsilon, so let's start with some, for every L, so it's a number, and for every epsilon, there exists some N0, so that if N is bigger than N0, and I have a set for every X in N, so with cardinality at least epsilon N, right? Then there exists A and B, such that A plus B, A plus L minus 1, B, all belongs to X. A, B is bigger than 1, right? So you can find that arithmetic progression with L elements inside X. As long as I have a set that's big, so it's a small part, but positive part of this. It has, so this was a theorem proved by Zemeradi. It was proved for L equals 3 by Roth. And then there were several advances, but then eventually by the early 70s was proved by Zemeradi for any L. It was a remarkable theorem that introduced the key idea of decomposing any set X into an ordered component where it looks ordered, and then we can imagine that in an ordered set it should be easy to find an arithmetic progression. And a chaotic component, it will be a part of the set that looks random. And both are fine, because an ordered thing naturally should contain arithmetic progressions, and a random thing should contain also. Because imagine that this is random, so any point A could be there with probability epsilon, right? And then but this is independent. So this event of this belonging to X would happen with probability epsilon to the L. As long as N would be much bigger than epsilon to the minus L, it should be there. So it would help to have chaotic things, will help. And if it's not chaotic, also helps, so great. Anyway, it was a little...
Ordered, you mean, has some structure?
Has some structure. It could be... have high probability in arithmetic. So there is some, I will explain a version of structure in a moment. I don't care about the one of Zemeradi because it's too complicated. But this theorem happened, but then it was, it progressed to a new version. So then there is Furstenberg, gave a new proof of this theorem. So how is the proof of Furstenberg? It translated to a different setup which gave first a version that is measure theoretical. So now the basic objects are like in that thing. So you have a map like this. Let's call it K. Right? So this is just a homeomorphism of a compact metric space. There is an invariant probability, right? Right? And now you have a set X with positive measure, right? And then it affirms that for every L bigger than or equal than 1, there exists B such that X this has positive measure. So the intersection of those translates of X, well, you iterate by time B, then you iterate more time B, and iterate a few times, and these all intersect at the same time. If you just do L equals 1, or 2, if you do just L equals 2, it stops here. This is the Poincaré recurrence theorem. For L equals 2, it's easy. For L equals 3, it's already, you need to work a little bit. All right, so the statement is that this has positive measure for some B. So this is the Furstenberg's theorem. And the point is that Renaud only proves this theorem, but shows that there's two statements you can go from one to the other easily, right? If you prove this theorem, you easily prove this one, and vice versa, right? So in a sense, the way it works in one direction is that if you had a source of a counterexample to this, so you'd have bigger and bigger sets of probability epsilon that don't have arithmetic progressions in it, you could pass through a limit that would be produce an object that's infinite, right? There will be some dynamical systems, and a set of measure epsilon that violates this. I'm not going to do the details, but the goal is to do like this. And how's the proof of Furstenberg? It is how do you prove this theorem? It's somehow similar to the idea of Zemeredi, of decomposing to order and cause, but I profit that I already talked about it. So you look at the Koopman operator, and there are two cases. It may have eigenvalues. If there are eigenvalues, then it's ordered. There is an isometry. An isometry, there will be iterates that go close to the identity. So basically, this is just essentially this, all the way. So you can get actually from probability epsilon, if this is at least epsilon, you can get this of size epsilon as well. This is basically all the same. From time to time, at the moments that you get close to the identity. So in the orderly case, it's trivial. And what happens if there are no eigenfunctions? Well, then it's weak mixing. There is decay of correlations, which means that basically for most big B, if you take B large, almost every large B, this is just independent events. So this will give epsilon to the L, right? So to give a positive probability that you can quantify. So those two extremal cases, all eigenvalues or no eigenvalues, give trivial answers. And there is still something to be proved, that is how to do both at the same time. So there is an extra complication, but the basic decomposition is very clear. How decomposing to order and chaos helps to prove the theorem. Anyway, that's the theorem of Furstenberg, and the same thing happens here. We are going to prove this theorem by finding, well, in a more easy way, because you could do it more complicatedly. We can do the simplest proof of this theorem is to pass through an infinite limit. So what gives the infinite limit? So there is an infinite dimensional version of our theorem, which gives you a dynamical system. So how to state the infinite dimensional version? You have, so now the data that you start is with a dynamical system that looks like this, but now n is in ZD. right? So it's an action, a commuting action that appears as natural here. This is a compact metric space. Those are homeomorphic, they commute. And there is an invariant measure, right? So this is given. And now given a continuous function, this is a small v, right? I can produce a measured family of Schrödinger operators by the following form. So H x, so I just need to define the potential, right? So this is the value of the potential. It depends, it's for every x in my space, which I sample according to this measure, Vx of n is just a small v of Fn of x. So I just follow according to my dynamical system. I sample the function, and this is my Vx, right? And this holds many cases. For instance, one famous case is the Anderson model. So for the Anderson model, it's recovered by taking, so Anderson model. What would put here? So we could put k is just minus lambda lambda to the z to the d. Let's say mi is just the Bernoulli measure. Not it's just the IID measure, the obvious measure, uniform measure. Here, uniform measure, and Fn is just the shift. And then you see that this is equivalent to the Anderson model. So a typical potential according to this, and a small v of x is just evaluation of the zeroth coordinate. If you put under this, I called it the Anderson model. But you could put any dynamical system. There are many interesting dynamical systems, quasi-periodic dynamical systems that I work on a lot, or any kind of dynamical system that you produce through an action. And you can always work in one dimension where you have a lot of dynamical systems. Anyway, so but that's the setup.
F0 means the coordinate of x?
Yes, so this, the x is a vector with values between minus lambda and lambda, and I just look at the zero coordinate. So since I consider here the shift, what you get when I evaluate this is just a random at everywhere is the different coordinates. Anyway, so that's just the claim. So that's a particular class of maps. And our theorem that's analogous to this theorem of Furstenberg is that, well, it has nothing to do with it, but just in this analogy. So this theorem is to that theorem as that theorem is to this one, right? For every Fn from k to k, and me, right? So any dynamics that I put, then for a generic v continuous function, for a generic continuous function, this the Schrödinger operator has no eigenfunctions. And for almost every x, the Schrödinger operator has no eigenfunctions. So here there is no need to talk about quantitative delocalization. I don't, because I am in infinite dimensions, I can just not have an eigenfunction. So I'm saying that if I look at this general dynamical setup, I can always achieve, by generic perturbation in effect, I can achieve delocalization in the sense that there are no more eigenfunctions. So we prove this theorem, and we can show that this theorem implies that theorem. So this is done like in one way, it's like this. And now I give an idea of how to prove the theorems.
What would be an example of something that only has eigenvalues? What would be a potential at maybe
A random one with a big disorder.
no, one that you can hook up.
So there are some examples that that work. If you take, so this is an example of Zhytomyskaya. So if you take sum, so the operator would be HUN equal UN plus 1 plus UN minus 1 plus a 3 cosine 2 pi n alpha. This has only, and alpha is 1 plus square root of 5 over 2. This guy has only eigenvalues.
There's no eigenvalues.
Huh? This is localized. It has a base of eigenfunctions. And if you take this, it has absolute continuous spectrum.
What?
It has AC, there are no this case has only eigenfunctions with 3. This case has no eigenfunctions. So this is one example. That, well, I need to justify why, but of course the spectrum of this operator is a Cantor set of positive measure, and that the eigenvalues are distributed in this. You don't have formulas for the eigenvalue. You can only prove that that there is a base of eigenfunctions. It's not trivial, this theorem. All right. So how do we prove this theorem? I find it interesting because a new technique that we developed, with this optimization technique, the idea is to, if you have an isolated eigenvalue, so this is just motivation. In the end, the proof just works, but as we try to prove it, we started with a few ideas. First, if you have an isolated eigenvalue, everything depends smoothly with respect to parameters. Right? You cannot, like the eigenfunctions will depend smoothly. You cannot, nothing catastrophic can happen. So you don't want to deal with isolated eigenvalues. On the other hand, you have many eigenvalues. So many of them are together, so that's not that bad. But more than that, you imagine that if the eigenvalues are very close together, then they will be easier to perturb. Imagine that then the eigenfunctions get confused if they are associated to one eigenvalue or another eigenvalue. One could be localized here, the other could be localized here. When they move together, they kind of get confused and some pieces go elsewhere. Maybe. So let's go for this. So then you get an idea that I want to change my potential to achieve something with respect to eigenfunctions, but maybe I should look at the eigenvalues to achieve that. So the way to do it is that I want to write expressions that will look like, let me give you one simple example. So there is one case that's very easy, but it's a little bit tricky because, for instance, the Zemeredi theorem is very easy to prove when epsilon is large. It doesn't mean that it's an easy theorem, but here it's also easy if you assume some things. I could consider as a function of eigenenergies, I could consider this expression here. So given V, a potential, it produces the spectrum, which are n to the d eigenvalues. And I can look at an expression like this that's an alternating sum of eigenvalues and look at what happens to this expression. Right? It depends on V. And like, if I make, so this is maybe positive, depending on how I wrote, but this is 0 if the odd, suppose that this has dimension, even dimension. This is 0 if the odd eigenvalues coincide with the even eigenvalues, in a sense. So I squeeze it together, the odd and even eigenvalues, this makes this small, which would be nice. So somehow decreasing this functional could be helpful because I'm putting together eigenvalues. Well, can I kind of effect a change of phi by changing V? So this is a question about the derivative of phi. So I need to compute the derivative of phi, right? And then there is an expression for which will involve derivatives of e's. So, but there exists an expression for the derivative of e. which is this very helpful formula. It's phi j of I squared. It's called the œHellman-Feynman formula. Feynman formula that gives this. So when you write this, the derivative of phi will have some combinations of those terms, but with signs, right? My goal is to see that the derivative is large. If the derivative is large, I can really change phi by making a small perturbation. But this will depend if I have cancellation or not.
So the derivative of VI is how you change the potential on the
Yeah, if I change the potential at site I, just by something, it will reflect on a change of EJs by this amount. Okay, so suppose, so first I have that sum of phi j I square is equal to 1, because it's normalized. The sum over j is equal to the sum over I, it's an orthonormal basis. So here, so the d phi, it basically has coefficients. It will appear terms like sum minus 1 to the j, phi j of I, and I want to know that this quantity, it has not a lot of cancellations, that basically I want that the sum now, when I sum over I, this should be large. If I can achieve this, then I can achieve a big change here, right? By just choosing, the sign here is unclear, but I can just make my perturbation on site I with the correct sign to achieve a big change in the end. But how do I avoid cancellation here? It's not clear in principle, because what I didn't say that I should have said is that I am trying to design a functional phi that should work in a neighborhood of my vector, of my potential. Once I perturb my potential, everything will change, right? And I need to perturb it again. But I need to have the same functional before. So whatever expression I write here, I should be able to show largeness in a neighborhood so that I can iterate the procedure and produce a flow. Anyway, I need to avoid cancellation. And there is a trivial way to avoid cancellation, which is supposing that there is too large localization. So if you assume that phi j of I square is not only not close to 0, but say is bigger than 1/2 plus c, some constant. If this happens, then I cannot have cancellation here. Because
How are they quantified? How are they quantified?
whenever I have that this is bigger than 1/2 plus c, you see that
J and I?
J and I are between, they oscillate between n1 and n to the d, right? But whenever I have one guy that's bigger than, so what I know is that sum of, you know that the sum of phi j I squared, if you sum over j, is 1. If you sum over I, is also 1. So this expression here, we'll have a term that has size 1/2 plus c, and the sum of all other terms is at most 1/2 minus c. So even if I don't know exactly which signs I put, I know that this will be bigger than 2c. So this implies that the sum of phi j I square with the sign incorporated is bigger or equal than 2c, which achieves my goal, right? So I can produce this uniformly to produce this flow. So I showed that localization, extreme localization of the eigenfunctions leads to a large derivative for this functional. But this depended on a very large localization. What do I do in general? So in general, it's more complicated. So I do like this, like Furstenberg did, and go through this other thing. So what appears? Okay, I try to conclude quickly. Is I pass through the limit, so I want to write an expression of the eigenvalues that will work. But in the end, in the limit for this object here, I have everything. The Hilbert space is infinite, so there are no more list of eigenvalues. What exists is the limiting distribution of eigenvalues, which done as follows. So you have an infinite dimensional operator. You can truncate the operator in a finite box. It produces a matrix. It produces a finite number of eigenvalues. They are there. The e's are here. And now when I do bigger and bigger truncation, I get more and more eigenvalues. And I can put the counting measure on the eigenvalues and pass to the limit. And there is a limiting distribution of eigenvalues. And there is n is the cumulative distribution. So n becomes a function from R to 0, 1. Right? So this is the cumulative distribution. So let's say, so if n of E, right, is equal to 1/2, let us say, it means that half the eigenvalues are less than E and half of the eigenvalues are more than E. So this is a kind of cumulative distribution. And now I can speak of the TIF eigenvalue. I can talk about the TIF eigenvalue. It's just like this. So now I have a counting measure for, I can talk about a continuous counting of eigenvalues, and now I can write an expression that mimics that one. So instead of writing sum of beta j ej, right, I write an integral of E, right, well, with some coefficients. So this is giving my position of the eigenvalue. This will tell that this is the TIF eigenvalue, and it will get a weight beta. And I integrate because every eigenvalue counts the same.
What is the Bj?
Beta, I need to find. Beta is a weight function that I need to find. It was just -1 to the j. That was extremely oscillatory. I have to, here there will be some continuous function that play this role. So this will have this will be my functional phi. And what I'm saying is that if I need to put beta, it's like -1 to the j, a very oscillating function to make phi, to control the size of phi. So if beta is oscillatory, so beta is supported in -1, 1, and if it does this, it should produce a small phi because there will be a lot of cancellation when you do the expression. And now there is a theorem that we proved that phi is C1 actually in the Banach space, and there is an expression for the derivative of phi. So phi is a linear, phi is a functional, and then when I apply this to a variation of my potential, it gives a response. It's given by a measure. Like there is the representation, so it's integral of w of x times a measure. This measure on my space, so w is a vector in my continuous functions. It's a continuous function here with the L infinity norm. So my response function, whatever I put here for his representation, is absolute continuous with respect to the invariant measure by the dynamical system. And there is an expression for psi of x. I need to assume that mi is ergodic here. And psi of x is equal to the integral of beta composed with n, integrate with respect to the spectral measure. So let's just take the output is that phi is something that I can control.
I forgot what psi of x was. Psi of x.
Psi of x, I'm saying that the derivative of phi, x on vectors. So it's a linear function, so it is the integral with respect to a measure. I'm saying that this measure is absolutely continuous with respect to the invariant measure, and I'm giving a formula for the density. The formula for the density is this one, where appears my coefficient here that I still didn't determine what I should put, and the spectral measure. Now the point is that this is what allows me to distinguish between localized and non-localized things, because I'm seeing here the spectral measure. And basically, if I have an atomic measure, I don't see cancellation. When you have an atomic measure, it's just a Dirac, let us say. It just takes the value at the Dirac, right? So basically, if you have any measure that has an atom, any measure, if it has an atom, then this atom, it dominates a neighborhood. It's the bigger atom in some neighborhood. Anything that you put that's just in this neighborhood cannot cancel the atom, because this atom has weight bigger than half of the neighborhood. It's like that situation. That was just a primitive situation. If there is an atom that takes almost all the probability it wins. But any atom dominates its neighborhood, if it's small enough neighborhood. So what I play in this game is that I produce a beta that finds that locates this atom. So there'll be a region dominated by an atom, and it just oscillates very quickly in this neighborhood. So when I write the beta like this, I manage to cancel phi and avoid cancel psi. So I get the inequalities that I want, that phi is under control, but psi is large, and it leads quickly to the contradiction. So the basic idea is to, after all this expression, you located exactly how to write, how to define beta to achieve, to create the flow. Okay, it's over time. I can explain more on questions.
So probably you can say something about the spectral measure, so you know that it's continuous. But
so in this case, we just conclude that they are continuous.
do you have conjectures or what it should be generally?
For one dimension, I have an old theorem that says that it's actually that there cannot be absolute continuous spectrum unless, except in the case that this is periodic. So when you have a periodic orbit, it's always absolute continuous. But in one dimension, generically, the spectrum is singular continuous with this theorem. We had proved already that it was not absolute continuous. We don't know how it goes in higher dimension, actually, about this. Another thing that's of notice is that me and I'm starting to I'm proposing actually that we should stop caring so much about ZT, and we should care about those finite dimensional objects. And the point is that some theorems that you have about ZT, they capture the behavior of big boxes, but actually not always. So ZT has a big problem that it doesn't have a sense of scale. Right, so let me discuss one thing. So you are interested in an object. So this is actually what I care about. It's a piece of iron, let's say, here. It looks like a box, and which I discretize. It could have a different shape, but it's definitely not infinite. Now, it has some size, about 1 meter. Right? And I care about the quantum dynamics inside it, so I care about my electron that is here, and maybe I care that the electron went from here to here after some time. I might care about that. But I have some, but if I look at the level of localization, or if I look at the level of ZT, localization, that's the traditional concept, it says that my eigenfunction is supported, so localization means supported on boundedly many on a set of bounded diameter. So since you are in ZD, it's infinite. You don't have a notion of scale. You just know what's bounded and what's unbounded. So when you say that you have an eigenfunction, it means that it's localized on finitely many places, so that it's localized at scale O of 1, big O of 1. So that's what localization cares about if I'm working on ZD, right? Now, from my point of view, of who just care about this matter-sized box, I care whether I can move for something that I can see, right? So the correct scale, that's the visible scale, is not small o, big O of 1. This is the atomic scale, it's the or the quantum Planck constant scales, the smallest structure scale where quantum effects are taking place at. But what I care is if I have a macroscopic effect coming from this, that my current was transmitted, and this transmission at some finite scale, at a finite length, it means big O of n scale. If I discretize this by size of size n, then small o of n scale, it means the difference between the visible and the invisible in macroscopically. And there's a big gap between big O of 1 and small o of n. And there is not only this big gap, that means that I need to understand it, as this is invisible in ZT. If I pass first to the limit of ZT, I lose the sense. I only have bounded or unbounded, and I lose things. So currently, I am trying to kind of find questions and examples and things like this that shows that really when you start looking at with a sense of scale, you have more interesting phenomena that appears for this bounded box models. So this depends on a lot of things. So this theory doesn't exist yet, but we found already examples, and we found some theorems that are interesting about that. That says of the importance of considering this new formulation of for Schrödinger operators.
You distinguish between square root of n and log n?
There could be distinctions between this, but the immediate qualitative, so this would be finer. So once you introduce the notion of scales, you can look at different scales and so on. But the first thing is to go between no notion of scale and some notion of scale. And then you can try to do so. Then there are many problems that are open once you start looking at this, at power scale, log scale, everything. But just let's put a scale to start with to play.
In the example of Schrödinger, this is on C.
Her work is on Z, yes.
You do this bounded scale?
No. Of course, if it's localized at the traditional sense, that's already very strong localization. I'm saying that even if I was not localized in the original sense, I could be seeing macroscopic localization. So macroscopic localization would mean that my eigenfunction gives a probability distribution on this box after I put it here. If my probability distribution looks like a Dirac, it looks localized. But looking like a Dirac means that it has support on small o of n. Doesn't mean that it has support on big O of 1. Of course, if I have support on big O of 1, I get this. But it's not necessarily this. So of course, she proved a strong theorem that implies localization. Of course, but I think that the notion of localization that makes sense macroscopically is this big O of n scale. But she gets everything already, but it's a particular model.
Little o of n.
She gets localization this scale. So it has support on this that's much better than that. So in particular it implies that. But you can imagine that there are situations that's not like this, that you have localization at this scale, but not at atomic scale. So you see things moving along many atoms, but not over big distance. And we produced some examples already with this very strange eigenfunction. So we produced eigenfunctions in dimension 1 that are supported on a Cantor set. So actually, the eigenfunction is in one dimension, but the support is a Cantor set. And this is interesting because it means that this state, it kind of has some Cantor tunneling. Like you can only find the state over this Cantor set, but as the dynamics evolve, the quantum evolution goes, it could jump over the gaps of the Cantor set, but not through any point, but only restricted to the Cantor set.
It's globally delocalized, but then
It is, it's spread out in a fractal set, and it has forbidden regions, but it can also tunnel. And this is the first examples that look.
delocalizing the contour.
Yes, there's some funny tunneling, yeah. Okay, so but I'm just advertising that there are many things that are to come once I have time to write, but there is actually not only theorems, but there will be a lot of open questions that will come from this new formulation that will be interesting to pick up on.
If you allow discontinuous potential, it's much easier to localize. You put barriers.
Well, you notice that my original problem has no continuity. It was discrete. What happens that once you go from discrete, it helps to understand that once you go from discrete to the infinite limit, it gives exactly this. This is exactly the setting that corresponds to the discrete setting. Right? It's not any ZT potential, it's the dynamically defined ZT potential. It's like in the Furstenberg theorem, Zemerad theorem is not analogous to any infinite theorem. It's a theorem of dynamical systems. Somehow, dynamics reappears once you introduce some kind of recurrence in the picture, it produces dynamics. So this is the correct theorem, analogous to that. And there is some continuity that appears automatically from that. It all comes together. You can work on L-infinity things, but they are not going to be connected to the actual objects of interest.